Hello and welcome to Lecture 4 of the Forces unit in Phys 1101. And in this lecture we're going to finally put together Newton's second law in its full vector form. So way back in Lecture 1 of this unit, we were looking at the motion of this cart, which I was pulling with an elastic. And we treated it as if it only had one force on it. And if you've been thinking critically about this, which I really hope you have been, then hopefully that sort of bothered you, because there should be other forces on it. Now, hopefully you agree that the elastic would be exerting a spring force on the cart. But that shouldn't be the only force, so let's think about that a little more carefully. So this is something we're going to work on more next time, identifying what forces act on something. But we'll get a start. So I'm going to draw this little circle around the cart, and the intent of this is that wherever the circle crosses some other object, that's telling us, oh, there's a point of contact. So the cart is in contact with the track, and it's in contact with the elastic band. And so all the contact forces will be due to those, right? We have contact forces due to the track and due to the elastic. And now we just have to think about what those are. Well, the elastic is the easy one. Elastic bands and springs produce spring forces, so I'll call it F sub S for a spring force. The track, well, that's a surface-to-surface contact. The surface of the track is touching the surface of the wheel, and so we know there will be a normal force, and there might be a friction. And friction is tricky, and let's not get into it in detail right now. I'll just tell you this would be a rolling friction. And then the other thing we need to think about is the long-range force. The only long-range force would be gravity, or in other words, a weight. And so those are all the forces on the cart. And so without going into much detail, because we'll do this next lecture, the weight would act down, the normal force would act up, the spring force acts in the direction that the elastic points, and the rolling friction opposes the motion, and it should be pretty small. So I'm going to draw it very small here. Rolling frictions are usually small. And one more thing, you might be worried about the fact that I'm not drawing on any force due to my hand. Surely I'm pulling on the cart, aren't I? Well, yes, but I'm pulling on it via the elastic band. My hand isn't touching the cart, and as I keep saying, I'm not a Jedi, so I can't directly exert a force on the cart. It's the elastic band that exerts the force on the cart. We've identified the other forces on the cart, and there they are. There's a normal, a weight, and a friction. But the net force still had to be to the right. Why is that? Well, because we already know from the motion diagram that the cart accelerated to the right. And so think about it. If the normal force had been bigger than the weight, then it would dominate over the weight, and the cart would accelerate up as well. Well, that would be strange. We wouldn't expect that. That would cause the cart to leave the track. Similarly, if the weight was larger than the normal force, that would be even stranger. The cart would have accelerated down into the track. So because we know that the cart accelerated to the right, we know that the weight and the normal force add to zero vectorially. So they're in opposite directions, and it turns out they must have equal magnitude so that they cancel each other out. And what we're doing here is just a vector addition. There is the vector addition of the normal and the weight and the spring force and the friction. And so there is our F net resulting from that vector addition. And I'm using this word F net, the net force. Net just means total. It's what you get when you add everything up. So just like when you look at packaging of something you're buying and it gives you a net weight, that is simply the weight of all the contents of the package, the total weight. So when we just have some object, here's some object, I don't care what it is, but it's got three forces acting on it like so. then to figure out which way it accelerates and how much, we don't just need to know how big these forces are, but we need to know their directions. And the acceleration is going to result from a vector sum. So I'm going to just write this as F1 plus F2 plus F3, whatever those forces are, all divided by m. But what that means is that I am taking the vector sum of those three forces roughly like that, with the forces I've drawn, to get a total force like so. And so that is the thing that we then call F net, the total force. This is F1, this is F2, this is F3. So this is F net over m. And you'll often see that written as the acceleration is the sum. So that's all this means, sum. Add all of them up of all the f's. This little subscript I on the f is just saying all of the i's over m. And so compare this. We had written this last time. This ignores all directions, so it's not sufficient. It tells you the proportionalities, but you have to pay attention to directions. And this sum of all the f's is the same as F net, the total force, what you get when you add all the forces up. Just another note on how we write the equation. When we write it this way, this is conceptually more useful because we usually think of the acceleration as the outcome of the forces acting on the object. And so this tells us how we get the acceleration from the forces by adding them up and dividing by the mass. But calculationally, we'll usually find it more convenient to write this equation rearranged this way, where all we've done is multiply through by m. So let's do a couple of examples. Here's an ice cube sliding down some sloped surface. And I've chosen an ice cube because as long as this surface is reasonably smooth, it means friction would be virtually negligible. And so what I would wind up with, if I do what we've been doing, is I would say, well, you know, the only thing that exerts any forces on this ice cube is the surface. The only contact forces would be due to the surface. And so we could have a normal, and we could have a friction that's sliding, so this would be a kinetic friction. But I'm going to say ice on a smooth surface, nah. Kinetic friction is negligible. And so what I would then have would be the normal force perpendicular to the surface like so. And then, of course, the long-range force, the weight being exerted on it by the Earth, points straight down. And now you need to take a vector sum of those. Now, we know something. This ice cube is not going to leap off the surface. It's also not going to fall through it. So the acceleration has to be parallel to the surface, either up the surface or down it. And so that will tell us how to draw this partly. We'll have the normal. And we need to get a result parallel to the surface, and so the weight must be of the right size compared to the normal to give us something that points, you can see, down the slope. And so there's our F net. F net points down the slope. And so that's the direction that the ice cube will accelerate. One more example. Let's say we have a Nerf ball. And I'm deliberately choosing a Nerf ball because a foam ball like this is going to have a force acting on it that has been present for other examples, but we've ignored it. But we can't ignore it for something like a Nerf ball, and it's air drag. So let's say this Nerf ball has been thrown, and it's no longer in contact with the hand of the person who threw it. And let's say it's going this way. All right, so there's its velocity vector. Note, I'm not attaching that to the free body diagram. Only force vectors get attached to the free body diagram. So this Nerf ball isn't in contact with anything except the air. And the air can exert a force on it. It exerts a drag force. So the drag force acts opposite the direction that it's going through the air, like so. So there's our drag force. And then, of course, there would also be a weight, because presumably we're doing this on Earth, or at least on the surface of some planet. Okay, and so now all we have to do is take a vector sum of those forces to find the direction of the net force, which is the direction that the acceleration would be. And so there we go, there's our vector sum, there's our weight, and there's our drag. And the net force then points down this way. And so that's the direction that the ball will accelerate, down and right, as it moves to the left.